So the topic of MOSFETs is almost done. So I was thinking of starting with op-amps because otherwise we will run short of time. Uh, do you want me to do questions of MOSFETs, or we can start with op-amp? Anyone can respond because we have done some questions in MOSFETs already. So what I will suggest is that you can start with gate questions on MOSFETs, and whatever your doubt is, please ask me in next classes. Okay, so you can start with MOSFET questions and try to do the recent ones. Those that are asked maybe after 2012, you can 2012 also is like 10 years paper, right? So maybe after 2015 16 also they had asked a lot of MOSFET questions. So after 2012 also you can look into MOSFET questions, whatever they have asked, try to solve it. I think in 2019 IIT Madras made the papers and some good MOSFET questions were there, so that also you can try out. Okay, I'm not sure which year it is, but I think IIT Madras made one paper which had good MOSFET questions for EC. Okay, so let's start with operational amplifiers. So three people have joined. So out of you three, do you know the basics of op amps, or should I start with numericals directly, or should I give you the basics of op amp? Anyone can respond. Okay. So Madhur Reddy is saying numericals. What about Chandrasekhar?
Yes, ma'am. You can start with numericals.
So basics you guys know, right?
Yes, ma'am. Yes.
Okay. So let me start then. So I will quickly give one or two formulas. I'll just write it down so that there is one brush up, and then we will start with some numerical questions that I have. Okay. So I don't have the gate questions with me as of now because I thought I'll first do the theory, and I thought I won't have time for gate questions. So I'll do general questions first, and then let me see if I can find some gate questions quickly, and we'll proceed that way. Okay. So first of all, just let me brush it up for you. So you know that this symbol that you see, this is the symbol of op-amp, right? And op-amp is a device that you get in market, you can buy it. Okay, so you would have done practical in your college and all those things. So the most common IC is IC 741, which is an op-amp, right? And is an op-amp IC. So what is inside op-amp is either through BJT or through MOSFET, you can design circuit that works as an op-amp. Okay, so this inside the symbol, basically if you want to understand it simply, there are circuits inside. Okay, and what you study in BTech or gate level is just a very simple operation of this operational amplifier, a very simple application you study. You don't go deep. Okay, so this is the electrical symbol of op-amp. Okay. Negative is the non-inverting terminal. This is the non-inverting, this negative is the inverting terminal. This is the non-inverting terminal. Okay. And when can the virtual ground concept? So there is a, okay, so first let me just write the open loop gain. So there is an open loop gain. That is, this op-amp is having a gain given by V out by V1 minus V2. Okay. So this is called the open loop gain, which is infinity for an ideal op-amp and having a very high but finite value for non-ideal op-amp. Okay. Open loop gain. Open loop gain and closed loop gain are two different things. Okay. Open loop gain and closed loop gain are two different things. So now second, the internal structure of the op-amp. So like we do make the small signal analysis model of MOSFET and all those things, right? We make an equivalent model. So the equivalent model, you can say, of an ideal of an op-amp is something like this. Okay, there is Ri. This was the negative terminal, this is the positive terminal. Okay, so that means between the positive and negative terminal there is a input resistance. Okay, and here we say there is a voltage controlled voltage source. Okay, and this is having a series resistance because it's a finite thing, it's a non-ideal thing. So this will have a series resistance R out. Okay, and this is the output terminal as well. Okay, V out, and V out you can, outside you can attach anything. This is V2, V1, and the difference between these two, V1 minus V2, is referred as VD. So in this VD, so this dependent source is dependent on this VD. Okay, this dependent source is dependent on this VD. So this is the equivalent circuit. For an ideal circuit, this Ri will be infinity, AOL will be infinity, R0 will be 0. Okay, but for a non-ideal circuit, these finite values will exist. Okay, so there is another, so two more important terms are there. First is, let me first say, slew rate. Okay, slew rate. So slew rate basically decides that if I change my input, suppose you are giving an input from any external, say you are giving it from an external signal generator, you are giving an input. Okay, now you are changing, that input is changing. Okay, suppose you gave a step. So the inputs changed from 0 volts to 1 volt. Okay, the input changed from 0 volts to 1 volt. So how fast is this transitioning happening? How fast is the input changing from 0 to 1 volt? You understand? When you will be giving it, suppose say from a signal generator. You're giving the input from a signal generator. So that there will be a rise time of this input, right? There will be a rise time of this input. This one is having almost like rise time 0. But if I say here, suppose it is having a rise time of 100 picoseconds. Okay, so this is what the change in input is. So what will op-amp do? If this input goes into the terminal of the op-amp, if this goes into the terminal of the op-amp, okay, this goes into the terminal of the op-amp, say, the output will be changing accordingly. Say I have connected it in a unity buffer fashion. Just check this for a moment now. So just check the circuit right now. So this circuit, what it will be do in this circuit, V out will be equals to V in. Okay, how, we'll see later, but V out is V in. So the question is that when I give an input like this, will my op-amp give the same output like this at the same time? An ideal op-amp will do, but for a practical op-amp, it will depend on its slew rate. Okay, it will depend how fast your capacitor output, how fast the capacitor, how fast the op-amp can charge this node. Every node in a circuit is a invisible capacitor. Every node in a circuit is a capacitor. Okay, it is getting charged. So how fast this capacitor will be charged by your op-amp, okay, this is decided by slew rate. This is decided by slew rate. So the bookish definition that you see, it is the maximum rate at which output voltage can change for a change in input. So that is what I just explained. For a change in input, how fast can the output voltage change? Okay, otherwise it will not show this kind of a thing. And what it will do, suppose it is going from 0 to 12 volt, your input, how your output will go, your output might go from 0 volt to, it will slowly keep on increasing, and your time has passed, right? Your input was like this, it has just reached 1 volt and it is trying to reach it, and we don't know whether it will be able to reach or not. Okay, so it will be very slow like this. Okay, so that is what slew rate decides. It is very important. Okay, and questions can come from this, and they have come in past. Direct formula based questions have come from past, but in future you can actually expect more graphical questions from this. Graphical questions can come. Okay, like input will be given and they will ask how the output will look like. Okay, graphical questions can be expected. Okay, so condition to prevent distortion for because of slew rate. Let us see condition to prevent distortion. Okay, so what I consider when we do this derivation, we consider we are taking a sine wave. Okay, so input I am taking as Vm sine omega t, where Vm is the amplitude. Okay, and V out, I know what is V out. V out is the op-amp's output. Okay, and that I am right now writing as the closed loop gain. Okay, the closed loop gain into Vi, because slew rate is something which is not going to come in open loop, right? It is something which is there in the feedback, so that's why I have taken the closed loop gain. Now what we were looking at, we were looking at the change of voltage, output voltage, and change of input voltage, right? Slew rate is all about the change in input and output voltage, right? So whenever there is the term change, we say differentiation. Now differentiating with respect to what? So we saw change with respect to time, how fast I am changing it, right? So change with respect to time. So dV out by dt. Okay, so you just differentiate this equation, you will get ACL Vm omega, right? This is what you are going to get, ACL Vm omega cos omega t. Is it true? Okay, so what will be the maximum value? Maximum value will be ACL Vm omega. Correct? Now I can also write it as, so normally if you see the slew rates value, because omega is what the frequency, right? The bandwidth, which is in megahertz. It is high, right? For the op-amp. So normally what we do, we write it in this term, ACL Vm omega by 10 to the power 6 volt per microsecond. So you will normally see in questions also that they give slew rate as, suppose, 7 volts per microsecond. So this is how you will mostly see it. When companies they sell op-amps, they give the specification in this manner only. So this is nothing but 7 into 10 to the power 6 volt per second. That high slew rate you need. Okay, this is the high slew rate that you need. Okay, so it is always in the range of your mega range, and you can call it as megavolts per second, or you can call it as volt per microsecond. Okay, okay then. So to prevent distortion, dV naught by dt max that we just found out, that should be always less than the slew rate. Okay, this should always be lesser than the slew rate of your op-amp. So suppose I have an op-amp saying 100 volt per microsecond, so I have to make sure that I will not give an input that will cause an output change that is more than that. Okay, so with that limitation, my change in input will also get limited. Okay, So now suppose I have a question. So let's do a question that the closed loop gain of an op-amp is 40 dB, okay, and the slew rate is 1 volt per microsecond. So what is the condition? What is the amplitude of input sine wave to prevent distortion? Okay, so what is the amplitude that we need to give to prevent distortion? Take f naught to be the frequency of operation to be 20 kilohertz. Okay, so please write down this question that an op-amp is there which is having a closed loop gain of 40 dB, slew rate is 1 volt per microsecond, f naught is 20 kilohertz. What is the amplitude of the input sine wave to prevent distortion? So simple, as we just saw the formula to it, right? dB naught by dt. So dB naught by dt is what? ACL Vm omega. So ACL Vm omega by 10 to the power 6. This is having unit of volt per microsecond. Okay, and that should be what? That should be less than equal to 1 volt per microsecond. Right, that this should be less than 1 volt per microsecond. So ACL, so 40 dB, 40 dB means what? So ACL is 40 dB, right? This is not in dB, this is in numerical. What is in formula? So since this is not power, this is voltage gain. This basically refers to the voltage gain, open loop voltage gain, right? So what this was found by, this dB was found by 20 log of ACL, right? So 20 log of ACL, this means ACL in numerical terms is 100. Is this clear? So ACL in numerical terms is 100. 40 dB means 100 of ACL, right? So 100 into Vm into 2 pi f naught. F naught is what? 20 kilohertz upon 10 to the power 6. This should be less than equal to 1. Can you solve and tell me what Vm you are getting? Anybody? Please quickly put in the values and let me know. Yes, so it is, no, it is not 0.78. You are doing some mistake. It will come as 0.079, yeah, 0.0795, which is equivalent to 79.5 millivolts. Please recheck your thing, Chandrasekhar. Okay. So now the next question is, suppose if your output is changing from minus 9 volts to plus 9 volts in minus 9 volts to plus 9 volts in, let's say, 10 microseconds, then what is your slew rate? If your output is changing from minus 9 volts to plus 9 volts in 10 microseconds, what is the slew rate? Can you tell me? So slew rate will be 18 upon 10, right? Because it's changing from -9 to +9. So 18 upon 10, so 18 volt per by 10 microseconds, and this is 1.8 volt per microsecond. Okay, now if this is what your input is, output is going through, this is what your output is changing. Now if the selected op-amp, suppose you have selected one op-amp, so if the selected op-amp's slew rate is 1 volt per microsecond, then you will experience, it will experience distortion. Okay, then you will experience distortion. If op-amp slew rate is greater than 1.8 volt per microsecond, then no distortion. So this is how you select the op-amp. Okay, is this clear? So then let me just move to the next topic. So if this is clear, I will move. Let me know. Please let me know once you are finished with this. Okay. Should I move forward?
Yes.
Okay. So now let us quickly see the frequency response. Okay. Okay. So frequency response of op-amp. So the graph that normally tells you the frequency response of op-amp is this one. So let me just write this as open loop gain. This one will be AOL. This is what the 3 dB bandwidth, AOL by root 2, this point, and this is the 3 dB bandwidth which gives you FOL, and this is the unity gain bandwidth, this one, right? Unity gain bandwidth, because the gain is unity here. So unity gain bandwidth. Sorry, this should not be. Okay, let me take this as 0 dB only, so this will be unity gain. Okay, so this is one. This is the line one, or 0 dB. You guys should well know Bode plots. Okay, in normally in control system subject that will come. Control systems, Bode plots is important. You should be very well versed in Bode plots and how to get the characteristics from Bode plot. That you should know. Okay. So how to solve the transfer characteristic, how to obtain it from, if you are given a Bode plot, you should know how to obtain it from Bode plot. So Bode plot, magnitude and phase characteristics, right? This, please revise these things. This will come handy with op-amps. And also, as I always say, KCL, KVL and transient analysis. This comes in network, right? So this you should first do. These topics you should first do if you want to appear for GATE. These are the topics that you first should complete. Okay, it's domain analysis and control systems network. So that is why I always say that before starting analog electronics, electronic devices, you should be well versed with networks, signals, and control. Network, signals, control you should first do, and then you go to analog. Okay, and then to digital. Digital is anyways not dependent on this thing. Analog electronics, after only these three subjects, you should start analog electronics. Okay. Okay. So op-amp is a direct coupled amplifier, therefore the voltage gain will remain constant at low frequencies, okay? But it will decrease at high frequencies due to capacitors, that the capacitance is effect, because inside the op-amp it is all MOSFETs or BJT, okay? So capacitances will come, and this is the effect that you are seeing right now, that there will be a decrease in the gain of the decrease in the gain with respect to the frequency. Okay, FOL that you see, that is also called as cutoff frequency or 3 dB frequency. It is also called corner frequency, break frequency. Okay, and it is also called dominant pole frequency as well. Okay, dominant pole is a term that you might come across again. Okay, the closed loop gain, so the gain at other frequencies is calculated with this formula. I'm not going to the derivation and all those things. Okay, F by FOL whole square, you will see that it matches the one that normally low pass filters will have. Okay, and at F equals to UGB, unity gain 1 equals to AOL upon under root 1 plus UGB by, sorry, I'll directly write UGB by FOL whole square. Okay, and UGB is actually very greater than FOL. In my diagram it might not appear so, but UGB is actually very far. Okay, UGB is actually very far, so UGB is usually very greater than FOL, and in that case you will see that this entire thing, this entire equation that I have written, it will be approximated as 1 equals to AOL FOL by UGB, and therefore unity gain bandwidth is also given as AOL FOL, and this will only happen for a single pole frequency, single pole op-amp or a dominant pole op-amp. If there are multiple poles present, then this is not true. Only for single pole this is true, and therefore for op-amps we try to compensate the op-amps and try to make their behavior as a single pole op-amp. Okay, even when multiple poles are present, we try to make the behavior as a single pole. This is beyond your scope right now. This is more into designing part, but you should just remember that for single pole or dominant pole concept, this thing is valid. UGB is equals to AOL FOL. Okay, that is if you multiply your open loop gain and your frequency, the 3 dB frequency, you will get the unity gain bandwidth. Okay, which is also called as gain bandwidth product. Okay, UGB is the highest frequency up to which the op-amp provides the amplification as well. Okay, so highest frequency up to which op-amp provides amplification. Okay, so till here you have written. Let me know. Let me know once you are done with this. Okay, if you have written it, please let me know. Should I move forward?
Yes, ma'am.
Okay. So the transfer characteristic of an ideal op-amp, transfer characteristics of ideal op-amp, okay, it will be, so if this is Vd and I have to plot V out, okay, what it will be? It will be a simple straight line. So from below 0 values, it will be saturating at minus Vsat, positive value, it will saturate at Vsat. This is your ideal characteristics. Okay, because you saw that the symbol was like this, right? So whatever input you give, this is the difference Vd, output is V out, and this is plus and minus Vsat. Okay, so the maximum voltage that the op-amp will reach is plus Vsat or minus Vsat. So this is the ideal characteristic. But with non-ideal characteristic, this shift will be gradual rather than the sudden step. Okay, and this is because of the presence of the finite gain, open loop gain. So in open loop gain was infinity, right? That's why you cannot see any slope here, right? Open loop gain was infinity, so you are seeing that infinite slope there, right? And uh, here the op-amp gain is finite, so you are able to see the slope. Okay, it will reach plus Vsat and minus Vsat, but it will reach with the gain, a finite gain. This region is called linear region, and this is called the saturation region. Okay, this is the output. So this is V out, this is Vt. Now, the interesting concept here is virtual ground concept in the op-amp, which you will be applying in almost all the questions. So what is virtual ground concept? The op-amp is nothing but an error amplifier. Okay, it basically takes the error and amplifies it. Why I am saying this? Because I have shown you that if I have two voltage V1 and V2 applied to the op-amp, the output is nothing but the multiplication by an open loop gain of the V1 minus V2, V2, right? That is the VD, V1 minus V2. So this is nothing but the error of the two voltage, right? So that is what the op-amp is doing. Now when I suppose I connect the op-amp like this, and here I apply V1 and I'm applying V0, right? So now what I'm doing, I'm taking the output and I'm subtracting it with the input, and that again amplified is giving me the output again, right? So basically what I'm doing, I'm taking the error and I'm trying to minimize it. Okay, so what this one is doing is V1 minus V0 into AOL equals to V0. This is what is basically happening here, right? This is what is basically happening here. So in a negative feedback, what happens is that you try to minimize this error between these two nodes. Okay, and therefore our target, so if you see now, V1 minus V0 is nothing but V0 by AOL, right? And therefore if AOL is infinity as with ideal op-amp, what is this error? It is 0. So basically you have succeeded and successfully you have passed on the input to the output. There is no error, right? And if there is some finite value present, then it will be approximately equal to 0, right? And that would mean that that V1 is approximately equal to V0, right? And now if I say that right now this configuration, since you saw it is giving V1 equals to V0, this is a buffer. It simply passes on the voltage. This is a buffer. We have another configuration here which can be used to understand that there is something like this, and you ground the other terminal, and there is V in here, and let's say these two are RR and this is V out. Okay, so you see that in negative feedback op-amp circuit, the difference VD, it will be so small that it can be approximated by 0, right? And therefore we come to the concept of virtual ground. Okay, so basically you can see that there is a virtual short circuit between these two nodes, right? Between inverting and non-inverting terminal, there is a virtual short circuit because VD is tending to 0, right? For a negative feedback amplifier, negative feedback configuration, VD tends to 0, and therefore I can say that a virtual short circuit exists between V1 and V2. Okay, and because there is a virtual short circuit between V1 and V2, okay, and one of the node is grounded, then the other node will also become 0, right? So what I'm saying is that there is a virtual short circuit between V1 and V2. There is a virtual short circuit between V1 and V2, and when I ground V1, I virtually ground V2. So this is what is virtual ground. I hope this is clear. So virtual ground is only applicable for negative feedback configuration. It is not applicable for positive feedback. In positive feedback, the virtual ground concept cannot exist because there is not a virtual short circuit. In that case, VD will go away from 0. It can never go towards D0. The main concept of negative feedback is that I am trying to make the difference between two terminals 0. And that is why when one of the terminal is connected to ground, the other terminal also tends to go to ground, and that is what virtually ground. Okay, so here V1 is 0, directly connected to ground, right? But V2 is not directly connected to ground, but it can still be taken as 0 volts because it is virtually ground. It is equal to V1 and therefore it is equals to 0 volts, and therefore it can be called virtual ground. It is not a physical ground. Physical ground is V1 and V2 is at virtual ground. So please understand the meaning very carefully. So this one is virtual ground. Virtually it is at ground. And this is a physical ground. So this one is connected. Physical ground. Is this clear? Okay. So the statement, suppose a true or false statement can come. That virtual ground concept can only be applied at negative feedback circuit. It's a true statement. Got it? So if till here there are no doubts, then I will proceed. Let me know. Is it clear? Shall I proceed?
Yes.
Okay. So after this we come at the two most common configurations of the op-amp. Okay. First that I just discussed. So here you see you are applying the input to the negative terminal through resistors, but you are applying it to the negative terminal. So this is the inverting configuration. I hope you know this. So inverting configuration. Okay. So quickly we will brush up. What we do, how we solve an op-amp circuit is, Suppose one node is at 0 volts, so this is at 0 volts, so I'll directly take this as 0. Okay, and then I apply KCL. So how I apply KCL? I take all the currents outgoing. So this current is going this side, this current is going this side. Let me say this is I1, I2. I'm going to very basic level and explaining. Okay, so what will happen at this node? Apply KCL at that node. What will happen? I1 plus I2 is 0, right? Because there is 0 current going inside the op-amp. Since we, okay, so I'm taking an ideal op-amp, okay? I'm taking an ideal op-amp, and therefore I believe that Ri is infinity. Ideal op-amp, Ri is infinity, therefore current inside the op-amp is 0, okay? So I1 plus I2 is 0. So what will be the KCL? KCL will be 0 minus Vn by R1 plus 0 minus V naught by Rf is 0, right? And if you solve this, you will get, and this negative sign shows that why it is called inverting, because it is 180-degree out of phase. V in is 180-degree out of phase with V out, right? Because of this negative sign. That's why that is called the inverting terminal. Inverting configuration, the input is at inverting terminal. Okay, this topology is also voltage shunt. It is a voltage shunt topology. Okay, I haven't gone through the feedback topologies. Feedback topologies you should read. In feedback amplifiers they will come because questions have come from them. So this is a voltage shunt. Voltage sampling is happening and shunt mixing is happening. Okay, I'm not explaining what are they. So voltage shunt topology. And from here you can also solve it in a second way, that when I said that this is a voltage shunt topology, then the gain is V out by I in. That is your gain. Okay, and the feedback factor beta is 1 upon gain, and therefore it is I in by V out. And in this case you can see that the shunt resistance is Rf, and therefore it will come out, if you solve you will see that it comes out to be 1 by Rf. Okay, and the gain, the closed loop voltage gain, will be given by beta into sorry, not beta into, but the in resistance into beta. So will be given by 1 upon beta R. R1, that was the input resistance, and it will be given by Rf by R. So you guys can try to derive this. Okay, check what is voltage shunt topology and see how the derivations are done, and try to derive this. I have 2022 paper. I'll just see that. Okay. So okay. So this was voltage shunt. So quickly let me just show you non-inverting, and then I will solve one question from 2022 paper as he was saying. So this is a non-inverting configuration. Okay, and in this you can see from virtual ground concept what will happen. If this node is Vi, positive node is Vi, then negative node will also be Vi, and then you will apply the KCL. Okay, so Vi by R plus Vi minus V out by Rf is equals to 0, and if you solve this you will get Vi into 1 plus Rf by R. Okay, this is a voltage series topology. the input is not in shunt, right? Input is not connected in parallel anywhere, right? So this is the voltage series. So voltage sampling is happening, but mixing is in series. Okay, so let me just find whatever question you are saying. 2022 you are saying, right? Just let me see if I have solved any of these. Mm, because I have solved a lot of questions for the gate papers. Okay, I don't think I have solved. So can you tell me the question number, Chandrasekhar, if you have any gate 2022 question paper?
Yes, ma'am. Yes, ma'am.
Okay, I'm downloading the paper anyways. So let's see.
Ma'am, question number 42.
42 you are saying, okay. Let me see. Hmm. Solution. That is fine.
Yes, ma'am.
Okay. You can see the question, right? Should I zoom it? So please take a photo of this and then we will start with the question. Okay.
Yes, ma'am.
I'm starting it then. So this is not a very difficult question, okay. I haven't taken any print. So wait. Yeah, you can see the screen, right? Okay. So now you can see that they have said that, as I said, that you should know how to solve Bode plot. So from Bode plot you can see that the gain at 0 is 12 dB, right? 12 dB at DC. Okay. Now at DC what will happen to the capacitor? Capacitor will be open circuit, right? So now what will happen? The circuit, how it will look? Right. So what is the value? V out by V in? that is 1 plus R, right? Because 1 by RF by R. Okay, so 1 by R, and this is equals to what? 12 dB, right? So since it is 12 dB, it will be 10 to the power 12 upon 20. 12 dB, that means 12 equals to 20 log gain at DC, and therefore gain is nothing but 10 to the power 12 by 20. Okay, from here I have taken this value. Okay, so 1 plus RF is nothing but R by 1K. So whatever R we will get it in kilo ohms. What is 10 to the power 12 by 20? Approximately equal to 4. Okay, so this implies R is nothing but 3 kilo ohms. Till here is it fine or any doubt? Then I will proceed.
Yes, ma'am.
Okay, so others, because Chandrasekhar is only responding, so others also I am taking that it is fine for you. Okay, okay. So now what will happen is I need the value of C also, because R and C they have asked. Now from where I will find C? So you see the information of 0 dB is given, the information of 3 dB is also given. 3 dB down, that is at 9 dB, log 10 omega is given as 3. Right? So at 3 dB down frequency. Okay, so 3 dB down frequency. So 3 dB down frequency is nothing but what? Log 10 omega C is what it is given? 3, right? 3 dB down is what? 9. That is how I am finding the corresponding 3. So please understand that 12 is your 0 volts, and I just showed at 3 dB corner frequency is there, right? So at 3 dB down from 12 dB, what is the value? 9. So at 9, what is the frequency? 3, right? 3 is the frequency at 9. So this is at log 10 omega. So that's why log 10 omega C is 3. This implies omega C is nothing but 1000 radian per second. Now how is corner frequency given by that? So RC, in a normal RC circuit, corner frequency is given by 1 by RC. Right? 1 kilo ohm you already have. Right? And then you have C, and then you have here 1000, 10 to the power 3. This implies C is nothing but 1 microfarad. Right? If you solve this, you will get 10 to the power minus 6, right? So answer is R is 3 kilo ohm and C is 1 microfarad. Is this question clear, or should I explain more? Please let me know.
Excuse me.
Yes.
Ma'am, at 3, like you have taken log omega C as 3 now, ma'am.
Huh?
In the similar way, like for 0, shouldn't we take like log omega C as 0, so omega C will be 1. Then in that case, it will not be a DC
So in
analysis.
Bode plot, what happens is that the DC is at 0 only. Okay. So this we take as 0 only. So this is at 1, 10, 100 and 1000. So where is your doubt?
Yeah, I mean, we have taken omega C, I mean omega is 0 instead of 1.
So the thing is that you can consider it as DC. So 1 hertz is the value, right? Frequency. So it's very low.
Yes, ma'am.
So capacitor, it will have a very low or very high reactance. So it will basically act as an open circuit only. So it is a kind of approximation we do. Okay, is this
Okay.
fine? So we take 1 hertz to be, so this is a good doubt he asked. So no, this is 1 hertz, right? But we take 1 hertz as 0 only, that is fine. That is a kind of approximation we do while solving circuits. Okay. So even if you want to take 1 hertz, you can take 1 hertz, and in that way you will have to assume that okay, capacitor value is usually like in microfarads. So in 1 hertz, the capacitor is showing reactance 10 to the power 6. So 10 to the power 6 reactance, if it shows, that means it is basically an open circuit, right? Okay. So then it is almost time. Then what I will do is I will take questions from question paper, and then we will directly start solving question next class. Okay. Because then I'm assuming that you guys already know operational amplifiers, how they are solved. So in that case, I can directly start solving questions. Okay. So this solution you have noted down, right? So there was one more question I remembered. Let me quickly just do that question. I don't know in which year it came, but this is the gate question. Can you see the question? So this is basically saying that there are two boxes, okay, F1 and F2, and this is your open. So now the F1 box has a characteristic like this, that it will pass something which is below FL. That is basically it is a low pass filter. And F2 characteristic is of a high pass filter. It will pass everything after FH. So the question was like this entire configuration, whether it is a high pass filter, whether it is a low pass filter, or a band stop filter, or a band pass filter. This was the question. This entire configuration. Okay. So simple. If you see, uh, yeah, the frequency of operation was given as, so the frequency of operation, uh, I think it lied somewhere between, I think it was, yeah, FH it was given, FH was greater than FL it is given. Okay, FH is greater than FL, that is what is given. So now if you take the frequency of operation, if you take the frequency of operation to be less than FL, case 1, okay, I am solving the question now. So my question was still here. So this was my question. This is my question. Okay. So now I am solving the question. So if F is less than FL, what will happen? F is less than FL. This means F is also less than FH. Since in question it is given FH is greater than FL. Okay. So everything will be passed, right? So V out equals to V in. Don't put a resistor here. This, let's say this is in U buffer condition. Okay, like this. Okay, so now everything is going to get passed, right? So because I don't remember the question exactly, let me just draw it like this. Yeah, this will make the question. This is the question. Okay, please take this question. So now if you see F less than FL, that means F is less than FH, and since F1 is a low pass filter, it will be passing the input, right? But F2 will block. So what will happen? F1 will be a short circuit, but F2 will be an open circuit because it is falling its in attenuation range, and it is going to plus, and minus is connected like this. So it is a buffer, so V out and V in. Okay, so in this case V out equals to V in. Pardon for bad handwriting. Okay, so is this clear what I did just now? If it is not clear, please let me know. So they have given the characteristics of F1 and F2. F1 behaves like a low pass filter, F2 behaves like a high pass filter, and they have asked whether this entire thing is a high pass filter, low pass filter, band stop, or band pass. Okay, so what you will do, you will take cases. So you have taken F. F is less than FL. Okay, that means F is less than FH also, because in question it is given that FH is greater than FL. Okay, so it is passing. Now let me take case 2. In case 2, let me take F greater than FH. So if F is greater than FH, the characteristic was like this. So FH, FL. So if F is greater than FH, it means it is greater than FL, because it is given that FH is greater than FL. So this is given. So that means now F1 will be an open circuit and F2 will be a short circuit. But input will go to this node, and therefore you will get V out as V in. Now let me take the next case. Okay, now let me take the next case. Case 3, where F is between FL and FH. So if F is between FL and FH, you can see that it is in this region, and therefore both the filters are going to be off. This is off, this is off, V out. So V out is nothing. Here I am not getting any input. V out is 0. Okay, so therefore the characteristic between FL to FH, you don't get anything. Okay, you don't get anything, but here you get a value, here you get a value, whatever is the value of V. Sorry, V out with respect to F. Okay, what is the maximum value of V? That is you are getting. This was a band stop filter. So this question was asked in GATE. Okay, I think it was asked for electrical students, but this is also one of the way how you can actually merge different domains together and ask questions. Is this clear? So then we will continue with Opamp and its applications in next class. We will do questions only, okay? And some questions I will try to find out from books also, some good questions, so that we can do that, okay? Okay then. If there are no more doubts, then I will close the session.